Transistors are active devices, electronic devices, semiconductor devices. They are used in the design of amplifiers, in the design of oscillators, and they are also having several other applications. There exist two main categories in semiconductor transistors. They are BJTs, or bipolar junction transistors, and FETs, field effect transistors. Bipolar junction transistors, their functioning is based on both the types of carriers, electrons and holes that exist in a semiconductor. That's why they are bipolar. There exist junctions. Their functioning is based on the junction properties. Two junctions exist in BJTs. That's why it is junction transistor. Transistor is a contraction of two words, transfer, resistor. The mechanism of gain involves transfer of current from low resistor to high resistor, low resistance to high resistance. Here, key or chief activity is transfer and resistor. By combining these two words, the term transistor was coined. So bipolar junction transistor basically provides gain. In its functioning, both electrons and holes play an important role, equally important role, and there exists two junctions in its structure. For this reason, they are called bipolar junction transistors or BJTs. These are three-terminal devices. They are labeled as emitter, base, and collector. Two junctions exist. They are named as emitter junction and collector junction. There exist three modes of operation: active mode, saturation mode, and cutoff mode. If we want amplification from the transistor, it has to be operated in active mode. There are three configurations: common base, common emitter, common collector. In common base is common for input and output. In common emitter configuration, emitter is common to input and output. In common collector configuration, collector is common for input and outputs. BJTs are capable of working both in analog domain as well as digital domain, but nowadays they are mostly restricted to analog domain. The digital domain circuits, they are using FETs for their design. Electronic devices, BJT-Basics series on semiconductor devices and circuits, lecture number 3.08. BJTs are bipolar junction transistors. These are electronic devices, active devices, widely used in the design of amplifiers and oscillators. They have applications in several other circuits and areas too. Even though they are widely used in analog domain, they have usage in digital circuit design too. In the present session, we focus on structural features, types, modes, and some other interesting aspects of BJTs are also considered. A few points regarding transistors. Notice these are points pertaining to all the transistors, not just to BJTs. Transistors are active devices. These are three terminal devices. Sometimes fourth terminal also exists. These are non-reciprocal semiconductor devices. These are widely used in the design of amplifiers, oscillators, digital circuits, matching purpose, etc. There are basically two types of transistors. Other types are also there, but they are not as important as these two types. They don't find usage as much as these two types find. One type is called bipolar junction transistors, in short BJT. Another type is called field effect transistors, FET. Now it is digital age. Everything is done, implemented in a digital domain. Out of these two, FETs are used in the design of digital circuits. BJTs, they are almost out of digital domain. At present, they are confined to analog area. Some important points regarding bipolar junction transistors. Both electrons and holes participate in their operation. As already told, transistors are semiconductor devices. Inside the semiconductors, there exist electrons as well as holes. Electrons are negatively charged particles. Holes are positively charged particles effectively. In reality, holes are not particles, they are simply vacant slots in the covalent bonds that exist inside the semiconductor. So both electrons and holes are found to participate, involve in the functioning of bipolar junction transistor. Transistor is a term created by contraction of two words, transfer resistor. BJT can be viewed as two diodes connected back to back. Two types of transistors are there, PNP, NPN. PNP is like this. P, P at both ends, in the middle N. NPN means N on one end, another end also N, in the middle P. So PNP transistor structure is three slabs, 2P and 1N. NPN transistor structure is 2N slabs, in the middle P slab, P-type semiconductor. In the previous point, it is told that BJTs are back-to-back connected diodes. Notice if we separate BJT in the middle, one can see on one side it is PN diode. Another side, a diode with the NP. So PN, NP. Two diodes. These two diodes, when brought together, when connected back to back, we have transistor structure. Same is the case with NPN. There exist three layers. These layers are called emitter, base, collector. The first one is called emitter, last one is called collector. In the middle, the layer is called base. So in PNP, emitter and collector are p-type and base is n-type. In NPN, emitter and collector n-type and base is p-type. There exist two junctions. One junction is called emitter junction, another one is called collector junction. Emitter junction exists between emitter and base. Here emitter junction exists. Collector junction exists between base and collector. Somewhere here it exists. In between base and collector. In NPN2, between emitter and base, emitter junction, between base and collector junction. So it is a 3-layer 2-junction device. Here is shown some information regarding structure and symbol. In A is shown NPN transistor. First N layer is emitter, last one is collector. In the middle, P layer is there, it is base. In between emitter and base, a junction formation takes place. It is called emitter junction. In between collector and base, another junction formation takes place. It is collector junction. Here it is required to be mentioned that even though emitter and collector appear to be similar or same, in reality they are not so. Emitter is heavily doped, whereas collector is not that much doped for optimum performance. To get good performance from the transistor, emitter is the one which is given heavy doping. It is not so with collector. So emitter and collector, even though appearance wise they are similar, they cannot be used interchangeably. Emitter can be used as emitter, collector can be used as collector. In B is shown the symbol of NPN transistor, base terminal, collector terminal, emitter terminal. One can find an arrowhead on a line which is representing emitter slab or emitter layer. In case of NPN transistor, it is outwards. It is pointing outwards. In C is shown PNP transistor. Here also emitter junction is there, collector junction is there. 3 layers, emitter, base, collector, all are available there in the structure. In D is shown its symbol, PNP transistor's symbol. Notice here the arrowhead is pointing into the transistor, into the device. In NPN it is outwards, whereas in PNP it is inwards. Some more points regarding bipolar junction transistor. It is a single crystal of semiconductor and is doped with one type of impurities on both ends and a different type of impurities at the middle. If p-type impurities are added on both ends, n-type impurities in the middle, resulting in PNP. If n-type impurities are added on both sides, both ends, and p-type impurities are added in the middle, then it is NPN transistor. The doping of the emitter is usually very large. Out of the 3 layers, emitter is the one which is heavily doped, and the base is the one which is lightest doped region. Emitter is heaviest doped, whereas base is lightest doped. In addition, base is also extremely thin. Here is a point regarding symbol, arrow direction in the circuit symbol. Arrow on the emitter head specifies the direction of current flow when emitter base junction is forward biased. So it has certain meaning, arrow. It is not arbitrary. There are modes of operation for BJT. 4 modes are there. They are called active mode, saturation mode, cutoff mode, inverse mode. What is active mode? When emitter junction is forward biased and collector junction is reverse biased, then it is called active mode. What is saturation mode? When both junctions are forward biased, then it is saturation mode. The transistor is said to be in saturation mode. Then what is cutoff mode? When both junctions are under reverse bias, then the transistor is said to be reverse biased. Then what is inverse mode? Emitter junction is reverse biased and collector junction is forward biased. Then the transistor is said to be in inverse mode. Out of the four, inverse mode is hardly used. Just for the sake of completeness, it is being mentioned. Only three are used. Out of the three, active mode is the one that is used in the design of amplifier circuit. In other words, if we want amplification from BJT, we have to operate it in active mode. Emitter junction under forward biased condition, collector junction under reverse biased condition. Remaining two, saturation mode and cutoff mode, they are used when transistor is used for switching purposes. When it is used in the design of switching circuits, their saturation mode and cutoff mode, they come into being. Here are given voltages across the junction. When transistor is in saturation, when transistor is in active mode, when transistor starts conducting, when transistor starts entering into cutoff region. Good amount of understanding can be had once we go through the table given here. Junction voltages on NPN silicon and germanium transistors at 25 degrees centigrade room temperature. For PNP transistors, the polarities assume opposite signs. So two rows are there. One row belongs to silicon, another row is related to germanium. First consider row pertaining to silicon. Let us start from right side. When a silicon transistor is functioning in saturation region, the voltage across collector and emitter, it is 0.2. So this is the meaning of VCE sat equal to 0.2 for silicon transistor. VCE means voltage between collector and emitter when transistor is in saturation region. When transistor is in saturation region, the voltage between base and emitter is 0.8 volts. When emitter junction is under forward biased condition, the voltage across base and emitter is 0.7 volts. The emitter junction starts conducting at 0.5 volts. The emitter junction enters into cutoff when the voltage is 0 across the junction. Starting point to cutoff is 0. If we apply 0.1 volts, 0.2 volts, 0.3 or 0.2 minus, all minus things, negative side, negative voltages, they drive the transistor into deep cutoff. Similarly, germanium. When the transistor is in saturation region, VCE, collector to emitter voltage is 0.1. When it is in saturation, base to emitter voltage is 0.3. When it is conducting, base to emitter voltage is 0.2. Emitter junction starts conducting when applied voltage is 0.1. The cutoff starts at minus 0.1 for emitter junction. If the voltage is minus 0.2, minus 0.3, minus 0.4, minus 0.5, the transistor goes on moving deep into the cutoff region. Here is shown modes of operation in a graphical form. A, B. Two diagrams are there. X-axis VEB, Y-axis VCB, VCB, VEB. A describes PNP transistor modes. B describes NPN transistor modes. When VEB and VCB both are positive, then the transistor is in saturation mode. When VEB is positive, VCB is negative, then it is normal mode. When VEB is negative, VCB is positive, then it is inverse mode. When both are negative, it is cutoff mode. This is for PNP. For NPN transistor, different modes are shown in B. When VCB and VEB both are positive, then cutoff mode. Both are negative means saturation mode. When VCB is positive and VEB is negative, then normal mode. When VEB is positive and VCB is negative, then it is inverse mode. Built-in potentials in open circuited BJT. As already mentioned, BJT can be viewed as two diodes connected back to back. Two diodes means two junctions. At the junction, there exists some potential. It is called a contact difference of potential. At the emitter junction, some potential. At the collector junction also, some potential. Both in PNP as well as NPN transistors. Those potentials are shown here. In the first left side part, potentials, V naught, contact difference of potential. It is positive. In case of PNP, it is negative in case of NPN. When the BJT is biased in active region. Active region means emitter junction under forward bias, collector junction under reverse bias. We have already seen in the previous slide, normally the voltage profile is like this. This is when the transistor is under open circuited condition. Now it is biased, forward biased on emitter junction. Therefore, voltage level of the emitter rises. Now, this is the voltage. Collector junction is under reverse bias. So, this is the fall of the voltage. This is the applied voltage. VEB is the applied voltage at emitter junction. VCB is the applied voltage at the collector junction. So, voltage levels change when junctions are biased. Here are shown minority carrier concentrations. First, consider PNP transistor. Emitter is P-type. So here we have plenty of holes. They are called majority carriers. Electrons also exist in the emitter layer. They are called minority carriers. There is a law known as mass action law. According to this law, hole concentration multiplied by electron concentration is a constant. Using this law, one can find minority carrier concentration. It is shown here. In base also, minority carriers, holes exist. That concentration is shown here. In collector also, minority carriers, electrons exist. Their concentration is shown here. Notice minority carrier concentration in emitter junction is low, whereas minority carrier concentration in the base region is very high. It is medium in collector region. Why? What is the reason? Reason is the emitter is heavily doped. The hole concentration in emitter layer is high. Therefore, minority carrier concentration, electron concentration has to be low, so that the product, hole concentration multiplied by electron concentration, remains fixed constant. Minority carrier concentration is shown for NPN transistor in right part of the diagram. Minority carrier concentration when transistor is biased. When it is biased in active region, whatever the things that are shown in the previous slide, that belongs to open or unbiased transistor. Here it is biased transistor. P-type emitter, N-type base, P-type collector. NP means electron concentration. It rises like this. PN means hole concentration. It is falling like this. NP again electron concentration, minority concentration is like this. NP naught means equilibrium value, electron concentration under equilibrium conditions. We have seen PN naught means hole concentration under equilibrium conditions. NP naught means equilibrium. These levels, equilibrium levels, we have shown in the previous slide. Now a few points regarding an important phenomena. It is called early effect. It takes place in BJTs. The collector junction space charge width increases, effective base width decreases with increasing collector junction reverse bias voltage. The modulation of effective base width by collector voltage is known as early effect. Consider PNP transistor, let us say PNP. As already mentioned, for obtaining amplification from the transistor, we have to bias emitter junction in forward direction and collector junction and reverse bias. It is already told that base is lightly doped, and when collector junction is reverse biased, then most of the transition region, it spreads into base region, very little into collector region or collector layer. It is due to light doping of the base. With increase in reverse bias voltage, what happens is the spread of the transition region across collector junction, it becomes more and more, and this more and more is in base region. Therefore, width of the base region or effective width of the base region decreases as reverse bias voltage is increased. It leads to certain serious consequences. It was first studied by Early, and hence it is called early effect. Consequences of early effect are with increasing collector junction reverse bias voltage, alpha increases, IPE, and as a consequence, IE increases. IPE means current due to holes in emitter region. It is a part of emitter terminal current. So it increases, resulting in increase in emitter current. Breakdown may occur in case of extremely large reverse bias voltage. So this is a serious consequence. Notice, suppose reverse bias voltage is increased further and further, then what happens? The spread of transition region in the base region increases. Ultimately, transition region may occupy completely the total base slice. Then base totally disappears. That situation is called breakdown. Now early effect in BJT is described here. WB is the base width, actual base width, but because of reverse bias on collector junction, a part of the base is being occupied by the transition region. After that, effective base width is no more WB, it is W prime B. It is less now. Now one can sketch minority carrier concentration in base region. As width is reduced, notice, as width is reduced, the slope of the curve is more. This is more. Slope of this fellow is more. When slope is more, what happens is diffusion current, minority carrier diffusion current, which is proportional to concentration gradient. It becomes more. With this, we come to the end of this session. In this session, BJT is introduced, its structure, its types, terminals, symbols, modes of operation, and also early effect. All these things are introduced and described. Hope this session is useful to you. We meet again in another session with a new topic soon.